How's exam 2? For exam 2, 15 points each question. Scores will be up this afternoon. Still have 1 or 2 folks to deal with exam 2, after which I will post the key. And I see that at least for a while we're going to have to operate with a wounded right side board. This massive weight you see over here is the counterbalance so that the board will go up and down easily. But each now and then these counterbalance weights fall out of the canal in which they're contained. In here we have the counterbalance weight for this board. From what I heard last night during last night's chemistry class, boom, this fell out. That makes this board stuck. Get it fixed as soon as possible. In any case, what we do now is to move along with stuff we've already been considering. How about that? Because all we have so far done is thermodynamics. And most of what you did in 2045 was thermodynamics related, except for kinetics. Equilibrium. Done a lot with equilibrium, haven't we? Equilibrium is strictly part and parcel of chemical thermodynamics. How so? We'll see. With the arithmetic we do, that is to say, in what we do in chapters 20 and 21, we'll make the arithmetic connection between equilibrium and fundamental thermodynamic properties for a reaction system. You learned about one of these already, didn't you? Enthalpy and change in enthalpy. You did that in Chemistry 2045. Unfortunately, there's a serious shortcoming with that consideration. So, I start this conversation by reminding you about this shortcoming. What we need and want to know about a reaction is, under the conditions at which the reaction is being considered, can it go? Yes or no? If it can go, then it's spontaneous. Now, what's the shortcoming? From a change in enthalpy standpoint, which is what you talked about in chapter 5 or 6 of the textbook you use for 2045, you cannot answer that question. Delta H is not a criterion for thermodynamic spontaneity. Because along with delta H, for any reaction system, you must also consider change in entropy. Symbol capital S. And with change in entropy, combined with change in enthalpy, by this relationship, we get the criterion for thermodynamic spontaneity, which is change in free energy. Just call it delta G, that's good enough. Symbol G, because J. Willard Gibbs, Josiah Willard Gibbs, a renowned physical chemist, at the start of the 20th century, early 1900s, developed these relationships. By serious thinking about the thermodynamic properties of a system, he came up with this stuff. Pretty good. So, G, because it symbolizes Gibbs. So a lot of times chemists will call this change in Gibbs free energy. Fine. What does it mean by saying the energy is free? Free energy.
Readily available and accessible. Readily available and accessible.
Well, principally available and acceptable.
Able to do work.
Able to do work. It's the amount of energy which you can get from a chemical system and use it to do work. But each and every chemical system is associated with a quantity of energy that the system will always keep within itself. You can't get that out of the system to do work. It's always going to be part and parcel of the system. What part of this puzzle relates to that? Entropy. That's right. As an example, a simple example, crude, but I think gives you an idea. If you want to cook an egg, you want to fry an egg at home on the stove, okay? You got a gas stove. So you turn on the gas and light it. Now, what do you want to do with the energy liberated from that gas flame? You want to transfer it to the egg, nothing else. But can you avoid heating the surrounding air? Can you avoid heating the parts of the stove which are in intimate contact with the heat, like the burner elements? Can you avoid heating the skillet? No. Because those are part of the system, and the system will contain energy in these parts of the system. Call it in the form of entropy if you like. So, of course, the flame itself keeps energy within itself, because the flame is material. Hot CO2 and H2O vapor mainly, because natural gas, principally propane as I recall, on complete combustion by reaction with oxygen gives you CO2 and water vapor. And those things which are components of the flame are going to keep some of the thermal energy within themselves. The water vapor, for example, which is produced by this combustion of the simple hydrocarbon propane. Well, what happened to the water vapor if it lost thermal energy? It would condense, become water liquid. If it condenses, if it cools even more, it becomes water solid. You have a hell of a time frying an egg with an ice cube, don't you think? Now, there's a lot of sophisticated thought that goes into this stuff. For our purposes, we will just try to get at the very fundamentals which will underlie the chemistry that we want to understand, which in the main is how these thermodynamic properties of a reaction system, delta S and delta H on combination gives us delta G, which then we will see how it relates, delta G, how it relates to equilibrium. And with that, we'll be able to take apart and analyze the system completely from a thermodynamic standpoint. Rather like we programmed ourselves to be able to do with acid-base systems, when along with equilibrium reaction considerations, we added material balance and charge balance. Well, now we're going to look at the fundamental thermodynamic puzzle parts of a reaction system so that we can analyze the system completely from a thermodynamic standpoint and get a better idea then of how all this stuff relates together, all this stuff with equilibrium. How then? Spontaneous. The criterion, once again, is change in free energy, delta G, for the reaction system studied under any imaginable set of conditions. If I take a sample of pure calcium carbonate and stir it up with a sample of pure deionized water, which I'll remind you is an investigation you performed in 45 Laboratory Assignment 4. Did the calcium carbonate dissolve spontaneously? Yes or no? Now let's review the investigation you performed. Remember assignment 4, you made some simple conductivity observations, conductivity measurements with this handheld meter gadget? And what kind of conductivity did you find for the laboratory deionized water? Did you get an on-scale conductivity reading? Not at all. Now, as we know, deionized water shows conductivity proportional to a total ion concentration at normal lab conditions of 2 times 10 to minus 7, right? This hydronium ion is 1 times 10 to minus 7 molar, and hydroxide ion is 1 times 10 to minus 7 molar. And the presence of each of these ions supports current flow. But our meters were insufficiently sensitive, or are insufficiently sensitive, to pick up the very, very weak, low conductivity of deionized water. Okay? Now then, you made some sodium carbonate solution, you made some calcium chloride solution. Then you were asked to put these two solutions together. As soon as you put these two solutions together, wham, out came this precipitate, right? What was the precipitate? A sample of teacher's favorite weapon. Sample of eggshells, oyster shells, calcium carbonate. And then you were asked to filter the calcium carbonate to separate the solid from the liquid part of the system. And then you were asked to wash the calcium carbonate with some squirts of deionized water to purify it. And then you took a small sample of this purified calcium carbonate and you stirred it up into a small sample of the laboratory deionized water. Do you recall doing this investigation? And after you stirred the the calcium carbonate with the deionized water for just a few seconds really, you wound up preparing saturated calcium carbonate solution, which you've done again this term in 46 laboratory, which we've done here in class. But then comes the $64 question regarding the issue that we are presently considering. You are asked to now observe the conductivity with our handheld meter of the saturated calcium carbonate solution, bearing in mind that the deionized water gave no reading, no observable conductivity. Did you get an observable conductivity with the saturated calcium carbonate solution? Did you? You did this experiment. Do none of you recall? Did you or did you not get an observable conductivity with the saturated calcium carbonate solution? Yes, you did. Well, and I assert that when you stirred the calcium carbonate into the water, that's all you did, was to give a chance for calcium carbonate to meet with deionized water. Some of it had to dissolve, right? Well, then, damn it, it dissolved spontaneously. How about that? But I know what you're thinking. At least my bet is I know what you're thinking. You're associating the word spontaneous with a material that is quite soluble in water. If I asked you if sodium chloride dissolves spontaneously in water, I bet you'd all say yes. And you'd be right. But now I'm asking you to recognize that by mixing calcium carbonate with water, nothing else could happen but some of the calcium carbonate dissolve. Nothing else could happen. You put together pure calcium carbonate with pure water. What else could happen? If you take pure sand, sand particularly soluble in water, you go to the beach and see all the sand disappear because it dissolved, and the ocean is 10 molar sand solution? I don't think so. But if you take pure sand and stir it with deionized water, the only thing that can happen is for some of the sand to dissolve. Now, the amount that dissolves to prepare saturated sand solution may be so damn tiny that you can't even detect it by measurement. But nevertheless, the only thing that could happen is some of the sand will dissolve. So did the sand dissolve spontaneously? Hell yes! I'll tell you a funny story about this, if I haven't told you yet. Chemists once did a study on the solubility of elemental tin in water. Tin. Took some pulverized tin, powdered tin metal. Okay? Shook it in enough deionized water to prepare 1 liter of saturated tin solution. So here we have this 1 liter of saturated tin solution. We filter to remove the undissolved tin, and we're looking at this solution. No solids contained within. And he labels it saturated tin solution. Okay? Then he did some arithmetic based on other measurements that he had made regarding the solubility of tin in water, which illustrated that. The amount of tin contained in the saturated tin solution was 1 atom. Would you say that's a very good illustration of something which isn't very soluble in water? 1 atom of tin, that's all that's in solution. And so, I'm going to take this 1 liter of saturated tin solution, and I'm going to pour half of it into a large beaker. So in the large beaker we have 500 milliliters of this saturated tin solution, and the remaining half liter of the tin solution I keep in the original flask. I give you the beaker, and then I ask, who's got the tin? How are you going to answer this question? Because I guarantee that tin atom didn't divide in 2 when I made the pour. So either you got the tin or I got the tin. How are we going to find out? It ain't possible. You can't possibly pick up this amount of dissolved tin, which is 1 atom. That's all. But in order to try to make the the spontaneous consideration on a far better criterion, or give it a more understandable basis, we prefer to study spontaneous from this set of conditions. What does the superscript 0 denote? Standard state. Do you remember learning about standard state conditions? You remember learning about some of these fundamental thermodynamic considerations in 45 laboratory? Which assignment? You all did this. I'm going to look up everybody's grade. I'm going to turn it into a flunk. I'm sending you all back to 45L and have you do this damn course, and this time learn from it. I try to get the administration of this university to realize this partnership stuff is stupid. That was done simply to accommodate registration requirements, enrollment demands. How idiotic. What this place is supposed to do is to serve education needs. And if we have to tell a bunch more parents that, sorry, we haven't got the territory available for your son or daughter, even though they're qualified, to come to school at the University of Florida this term, so be it. I'd much prefer to do that than throw education quality down the drain, which is what happens when we have you in there working in teams. Because it winds up being a case where hardly anybody learns anything. It's not your fault. I don't blame you. But in assignment 7 for the solutions experiment, I purposely wrote about all these fundamental thermodynamic considerations because they're damned important. And one of these fundamental thermodynamic considerations was the recognition that the simplest, best criterion for thermodynamic spontaneity is to base it under standard state conditions. Do you remember what standard state conditions are?
298K.
The first remark I heard was 298K, and that remark is wrong. But that's okay, I thank you for responding. There's no such a thing as a standard thermodynamic temperature. None. You can do standard state studies under any temperature so long as the system components are stable under those conditions.
Everything in the state of the most stable, so like oxygen is diatomic.
Well, if you're going to put it this way, you're going to go and be talking a whole lot of stuff. So I'll put you on hold. But it's all right, you're on the right track. For starters, standard state conditions mean that every system component is present. That means reactants as well as products. And for solution species, the concentrations for solution species under standard state conditions is how much? 1 molar. So if I want to answer the question, does sodium chloride dissolve spontaneously in water from a standard state standpoint at NLC? I go to the laboratory, which temperature-wise is practically NLC. Take that as 25 centigrade, but the laboratories usually run about 22, 23 centigrade. 25 centigrade, a little bit warm. And I take 1 molar sodium chloride solution, because in 1 molar sodium chloride solution, I've got sodium ion at 1 molar and chloride ion at 1 molar, correct? And I add to that sodium chloride. If the sodium chloride dissolves, then the sodium chloride is dissolving under standard state conditions. If I wanted to find out if calcium carbonate dissolves under standard state conditions, what would I do? Make a parallel to what I just told you. I would attempt to prepare a system in which the calcium ion was present at a concentration of how much? And the carbonate ion was present at a concentration of how much? And what would I find out in trying to prepare this system? Can I prepare this system?
No.
Hell no! As soon as I bring the calcium ion and carbonate ion species together at a molarity which exceeds 1.4 times 10 to minus 4, because that's the molarity of calcium carbonate and saturated calcium carbonate solution, wham! Out comes calcium carbonate. So now I know calcium carbonate can dissolve spontaneously from a delta G standpoint. If I take pure calcium carbonate and pure water, the calcium carbonate will dissolve. We just talked about it. You did this investigation in assignment 445L. But from a delta G0 standpoint, absolutely not. Simple reason why: I cannot make 1 molar calcium carbonate solution.
Wouldn't there be virtually no carbonate, because all the carbonate would turn to hydrogen carbonate, bicarbonate?
Well, if I take highly concentrated carbonate ion solution, it's mostly carbonate ion.
But this is very low concentration.
What is that? Well, what I'm saying is, I'm going to take what I'm going to do, okay? Here's the way I'm going to try to prepare 1 molar calcium carbonate solution. I'm going to take 2 molar calcium chloride solution and 2 molar sodium carbonate solution, right? These I can prepare, because calcium chloride and sodium carbonate are each quite soluble materials. And then I'm going to put these solutions together in equal volume ratio, because the dilution factor will wind up after dilution giving me 1 molar calcium ion and 1 molar carbonate ion, right? Provided no reaction occurs. But a reaction will occur, won't it? And out will come big bunches of calcium carbonate. Okay? So, when we talk about spontaneous from a standard state set of conditions, we have a specific reference point, because the system contains all components and everything's present under standard state conditions. So let's extend the review of standard state conditions. Solution species, each present 1 molar. And you see what happens. If it makes precipitate, then the stuff in question does not dissolve spontaneously under standard state conditions. If I don't make precipitate and I dissolve more solid, then it does dissolve under standard state conditions. Like the sodium chloride, which does dissolve under standard state conditions, and the calcium carbonate, which does not. Gases. If gases are part of a system, and I choose to study the system under standard state conditions, what must be the partial pressure of each gas in the system under standard state conditions? 1 atmosphere for each gas. So if I have a 2-gas component system, then each gas is present at a partial pressure of 1 atmosphere. Therefore, the total pressure on the system is how much? 2 atmospheres. Okay? And the only other remaining part of the standard state condition is the easiest part. Because the chemical system can contain solution species, solutes. It can contain gases. And it can also contain pure liquids or pure solids. That's it. There's nothing else, right? Gases, liquids, solids, and dissolved stuff. Nothing else. The dissolved stuffs, 1 molar. The gases, each present at partial pressure 1 atmosphere. And pure liquids and pure solids, which by definition are in the standard state. How about that? So if you're studying a reaction system which involves a solid or a liquid, just put them in. However much might be required by the reaction equation and the coefficients which it shows. So if I take this to be pure calcium carbonate, here's a sample of standard state calcium carbonate. Doesn't make any difference how big the piece is. Tiny speck, a mountain. Standard state calcium carbonate. Piece of iron, standard state iron. Now then, more on spontaneous. Water liquid going to water vapor, NLC. Water solid going to water vapor, NLC. Or I can add water solid going to water liquid at NLC. So let's call this 1, 2, 3. Water liquid, water vapor, water solid, water liquid, water solid, water vapor, all at NLC. Which of these transformations are guaranteed to be spontaneous? I'm listening. Well, let's put it this way. At NLC, can I have water solid? You did study phase diagrams for water, and we had you look at this previously because I asked you a question about this in times past. We're going to be looking at this again in great detail, probably next gathering. At NLC, which is a temperature 25 centigrade, water solid, ice cannot exist, period. I don't care the pressure you exert on water. You cannot get it to solidify at this temperature. If my memory's right, the highest temperature at which ice solid, water solid called ice can exist is 0.01 centigrade. That's it. Because that's the temperature at which the triple point for water, the common triple point for water is observed. Remember what triple point is? What's triple point?
All 3 phases exist at once.
It is a pressure and temperature condition set at which all 3 phases exist. And for normal water, those phases are liquid, solid, vapor. But water shows a bunch of triple points. But at the other triple points, you have equilibrium between water solid and water vapor. No more liquid. If you don't remember that, we'll be looking at that soon at the phase diagram. When we look at the phase diagram. Okay? Now then, what about 1? Is that spontaneous? Right here in this room? We already discussed what would happen if I made a mark on the side of my cup indicating the meniscus level of the water liquid contained within. And if I were to leave this cup here with the amount of water which is presently contained within, and we come back on Monday and re-observe the liquid level, the meniscus liquid level, would the meniscus liquid level be the same, higher, or lower? Probably be gone. Because the air conditioning system in here does not allow the air atmosphere to become saturated with water vapor. Because when the air atmosphere is saturated with water vapor, what condition exists from a weatherman standpoint? 100% relative humidity. And it ain't pleasant to sit about in 100% relative humidity conditions. Because as we engage in this natural, human, physiological, chemical action called perspire, we sit here and stew in our own juices. Because we're going to continue to perspire, but now there will be no net evaporation of the perspiration beads of sweat from our surface. So we're going to get more and more gooey in our own juices. Ooh. But the air conditioning system does not allow that to happen. Doesn't allow the air atmosphere to get saturated with water vapor. Tell me. In this direction, this transformation shows evaporation of water liquid, doesn't it? And in this direction, it shows condensation of water vapor to water liquid. What property of water measures, water liquid or any liquid, measures its tendency to evaporate? What property of any liquid or solid measures its tendency to evaporate? Vapor pressure. What property of a gas measures its tendency to condense? I'm listening. You did this in 2045. You think it might be a property of a gas which is a measure of its concentration? Do you think the higher the concentration of a gas, the more likely it might be to condense? The higher the concentration of the gas. Partial pressure, you betcha. So if we're observing this transformation at NLC, the only way this thing can come to equilibrium is when the vapor pressure of this stuff, its tendency to evaporate, becomes exactly equal to the partial pressure of water vapor, its tendency to condense. Now, let's ask the same question from a standard state condition standpoint. Because under standard state conditions, what's the partial pressure of this stuff? 1 atmosphere. Tell me, at what temperature does this stuff develop a vapor pressure of 1 atmosphere? What is it? 100 degrees centigrade, the normal boiling point temperature of water liquid. Did you not learn in 2045 that the normal boiling point temperature of a liquid is that temperature at which the liquid will have a vapor pressure of 1 atmosphere, you betcha. Now then, how about this? This is spontaneous transformation at NLC. If I hand you a beaker of water, a large beaker of water, or a large beaker with a lot of water within, say a few hundred milliliters, and I give you a big chunk of sodium, and my direction to you is to drop the sodium in the water and take a look to see what happens. Beaker, sodium chunk, drop, looking to see what happens. Would you do that? No. Why not?
It's a violent reaction.
A violent reaction. You remember seeing this violent reaction illustrated for you? Yes. 2045, assignment 5. You were asked to view a short video before you did the lab work for assignment 5, part 1, where you had the pleasure and blessing of watching a very famous movie star do this for you as a demonstration. That movie star is a very fortunate person because he looks just like me. How about that? In World War I, one of the first attempts the Allied forces made in building depth charges was to make them out of sodium. Unfortunately, sodium concussion on reaction with water goes pretty much straight up. So if it didn't drop the depth chart just right, so the U-boat sails over the depth chart, boom, you didn't get the U-boat. U-boat over here, boom, miss. U-boat over here, boom, miss. So they try to make better depth charges, which blow out this way. How about hydrogen with oxygen to make water liquid? Or water solid or water vapor? Is spontaneous? You ever hear about the dirigible Hindenburg? 1937, over Camden, New Jersey. German quote-unquote airship, because it wasn't filled with air. What was it filled with? Hydrogen. Because of its very low density. Hindenburg came across the Atlantic Ocean, no problems whatsoever. But it got into a bit of a storm condition over northern New Jersey before it was able to moor. What happened as a consequence of the interaction of the Hindenburg with the storm conditions? Tore a hole in the Hindenburg skin, and out began to leak the hydrogen. Hydrogen mixing with oxygen from the air. There were some power lines in the vicinity as well, although it might have been set off by lightning strike. And once the hydrogen-oxygen reaction started, whoosh! No more Hindenburg. Spontaneous? You're damn right. So, under normal lab conditions, this presents an example of a non-spontaneous reaction. It won't go in that direction, but some non-spontaneous reactions, under the conditions under which they're being observed, can be made to go, whereas some cannot. For example, we talked about solid becoming vapor for water or solid becoming liquid for water at NLC. Can you make this go in this direction at NLC? Nothing you can do. You can't make water solid at NLC. Can you make this go to solid at NLC? No, impossible. You can make this go to liquid, but you can't make this go to solid. On the other hand, at NLC, can I make this go to these materials? Here's a process by which I can make this go. Omega. You know what omega symbolizes? Electrolysis. I put a little salt, like sodium sulfate, something like that, in the water to give me something that will support current flow. And I run electric current through it. And I will find that at the cathode, I will make hydrogen gas, and at the anode, I will make oxygen gas. An electrochemical phenomenon, which we'll discuss in detail when we get to chapter 22. Now then, more on the parts of thermodynamics. From the first law in thermochemical studies, where you're really studying heat flow, and I'm sure in 2045 you symbolize that with small q, you get delta H. Tell me, when you measure delta H for a reaction system, what is the most important property of the components of the reaction system which you discover by measuring delta H for the reaction system?
Stability.
Tell me more.
Bonds.
Exothermic.
If a reaction is exothermic, heat liberating, what may you now fairly conclude about the products compared to the reactants? What?
Stronger bonds.
Stronger bonds and perhaps also more bonds. Bond improvement. Exo means bond improvement. From a bond strength standpoint, reactants become more stable as they convert to, well, I shouldn't say it that way. The products are more stable than the reactants from a bond strength standpoint for an exo reaction. Endo reaction opposite. Because an Endo reaction requires that you input heat. And when you input heat into any sample of matter, do you make bonds stronger or make bonds get weaker? Weaker, of course. But as we've noted, del H by itself is not a criterion for thermodynamic spontaneity. So we got to go to the second law. Second law tells us this, which really is the first criterion used by chemists and physicists for thermodynamic spontaneity. Because the second law says the change in entropy for the universe, I wrote it over here, is positive, which means a favorable change in entropy for each and every spontaneous process. Now then, quick, let's take a look at this. At NLC, this is spontaneous, isn't it? But does this transformation, which is spontaneous, proceed with bond improvement or bond disimprovement? Bond disimprovement. Del H for this thing is endo plus, but still it's spontaneous. Why is it spontaneous? Because the far more favorable entropy of water in the liquid phase outweighs the lower entropy for water in the solid phase, which causes this to go and winds up making this larger in magnitude than this. Now, an illustration of this universe law. Let's go back to water liquid becoming water solid at minus 10 degrees centigrade. Now, I don't know what the operating temperature is of your refrigerator freezer, but we know it's lower than 0 centigrade. Let's say it's minus 10 degrees centigrade. Now, clearly, this is a process driven by delta H. But does this process proceed with an increase or decrease in entropy? Decrease. Would you recognize right away that for a given type of material, its entropy is always lowest when it's solid and highest when it's vapor? Right. You can look at entropy as a relationship to how the component particles of the sample can move around. Well, in the solid state, I can't do anything but vibrate. But in the liquid state, I can vibrate and I can rotate and I can move over here and here. But in the vapor state, I can do all these things and move up as well. Just as well as sideways or moving down. So I have a greater freedom or range of motion in the vapor state, which is why I have the highest entropy. The question is, and we'll answer this at the start of the next gathering, this process is spontaneous, and it proceeds with an unfavorable change in entropy. How can it be then that the change in entropy for the universe is positive for this process? You follow the question? This process proceeds with an unfavorable change in entropy, yet it's spontaneous, which means the change in entropy for the universe has to be positive on the increase. How can this be true? Very simple. The answer's in the notes. We'll pick it up from this point next time.